reaction is at equilibrium. It will stay at equilibrium until that system is messed with. Once we apply a stress to a system at equilibrium, the solution or the equilibrium position will shift, and then equilibrium will then be reestablished. So what we're going to look for in this and be able to predict through the Chateliers Principle is which way the reaction is going to shift that first time before equilibrium is reestablished. And when I say equilibrium is reestablished, it will have the same K value for its equilibrium constant. So predicting the direction of that first shift, so don't think too far into the future. We're going to follow the Chateliers Principle. If a stress is applied to a system in equilibrium, the system changes in a way that relieves the stress. So there are really only three stresses that we need to talk about. The first stress is going to be changes in pressure. It only affects systems with gases. Solids and liquids are not really affected by pressure, and really when we're dealing with equilibrium expressions and constants, we only have to worry about those in aqueous solution. And it is only going to affect those systems of gases when the total number of moles on the right does not equal the total number of moles on the left. So there has to be a difference in the number of moles on each side of the reaction. Increasing pressure will favor the side with the fewer moles. So if we're squeezing something down, it is going to shift to make itself smaller and shift to the side with fewer moles. Again, we can look at that based on the coefficients of the values within the balanced equation. Changes in concentration. If we have an equation, A plus B are reactants going to C plus D, and this thing is in equilibrium, so it is shifting back and forth. Increasing the concentration of A will cause an equilibrium shift to the right, and the concentration of B will decrease. So as we increase or add more of a reactant, we have more that is available to make products. So the forward reaction will be favored, which means the reaction will be shifted to the right. Since I also have more A, it is going to combine with more B, and so the concentration of B will decrease as this equilibrium is shifting. So just a few things to remember. Add shifts away, so it's going to shift away from the thing that you added. Up here, in this mock equation, we talked about increasing A. If we add A, it is going to shift away from what we just added. And remove shifts towards. Again, I have both of these starred. These are little things you want to remember. So if I remove something, it is like digging a hole in dry sand. If you remove like C, and we would do that through precipitation or something like that, and get those particles out of there, the reaction would shift towards what you just moved. So again, in this little instance, if I removed C, the reaction would shift towards what I just removed, or the forward reaction would be favored, or there would be an equilibrium shift to the right. Our last stress is going to be changes in temperature. Adding heat shifts equilibrium so that heat is absorbed, so it's going to favor an endothermic reaction. So we might have something like carbon plus oxygen is going to give us carbon dioxide. And if I, let's see, let's put heat in here. Sometimes it's written like this, sometimes it might just say heat. And let's say this is equilibrium. So what this says is that in the forward reaction, carbon plus oxygen produce, and that's how we read the arrow, carbon dioxide and some heat. So the forward reaction here is exothermic. If we read it the other way, it says that if you take carbon dioxide and add some heat, then you are going to break it down into oxygen and carbon. So the reverse reaction is endothermic. It requires heat in order to get the reaction to proceed. So in this case, if we increase the temperature to this reaction, then The endothermic reaction is going to be favored because that's the one that needs heat, and the reaction would shift to the reverse reaction. If I decrease the temperature, then the reaction would shift to the forward reaction. Decreasing temperature would favor the exothermic reaction. So this is something you want to remember with equilibrium shifts.